In this tutorial, we are going to cover the following objectives. First, calculate the equivalent resistance of a network of resistors that can be broken down into series and parallel combinations, and calculate the voltage, current, and power dissipation for any resistor in such a network of resistors connected to a single power supply. Hello, welcome to another episode of Physics is Easy with Mr. Jesse. Before we start solving problems related to our objectives, let us first recall the equations that are related to current, voltage, and resistance of series and parallel circuits, and these equations are summarized in these two tables. I would just like to highlight on the equation for the equivalent resistance of a parallel circuit. So if you have trouble solving for the equivalent resistance without a calculator, it would be very helpful if we could express these two equations in this format, which is called product over sum rules. If you have two resistors, that would just be R1 times R2 divided by the sum of R1 and R2. So that is why it's called product over sum. And if you have three resistors, that's going to be the product. So that's R1 times R2 times R3 divided by, now the sum would look a bit different, but because it's going to be R1 times R2 plus R2 times R3 plus R3 times R1. So again, this is how we could also solve for the equivalent resistance of resistors in a parallel circuit. In this lesson, it is also very important to recall Ohm's law and the equations for power. So for Ohm's law, we have voltage is equal to current times resistance. So if we would want to know the voltage across the first resistor, that would just be V1 is equal to current 1, or the current through the first resistor multiplied by the resistance of the first resistor. Similarly speaking, the total voltage is just equal to the total current multiplied by the total resistance, or the equivalent resistance. On a similar note, power, which is P, is just equal to IV. So if we would want to solve for total power, that would just be total power is equal to total current plus the total voltage. Or if we would want to know the power that is dissipated in resistor 1, we could just say power dissipated by the first resistor is just equal to the current through the first resistor multiplied by the voltage of the first resistor, or we say P3 is equal to I3 times V3. And recall that we have several forms of the equations of power. So we have P is equal to I squared R, and we also have P is equal to V squared over R. Now let us solve a sample problem. Consider the combination of resistors shown in the figure below. Find the equivalent resistance between point A and B. Now the term equivalent resistance is just very similar to total resistance, or RT. So basically, points A and B are points in the circuit with different potential difference, and when there's potential difference, there's current because it's going to cause charges to flow. Now before we would trace the flow of our charges, it is important that we will label our resistors. So if our 12 ohm resistor is resistor 1, this could be our resistor 2, resistor 3, resistor 4, and resistor 5. You could name it the way you want. It doesn't really matter. So now again, as I have mentioned earlier, because points A and B rather are of different potential difference, so charges could either flow from A to B or from B to A depending on the type of current, whether it's conventional or electron flow. But in this case, it doesn't really matter. So let's assume that charges will start flowing from A. Alright, so they will start flowing from A, and when they reach this junction over here, some charges would go up and other charges would go down. So we are actually confronted with two paths of the charges. So this means that resistors 1 and resistors 1 and 2 rather are in parallel. So they're in parallel because charges would be flowing through them in different paths. Now, as charges flow through resistor 1 and these charges flow through resistor 2, they are going to meet at this particular junction. And then all of them are going to pass through resistor 3 until such time that they're going to reach this junction here. So again, some charges would go up, other charges would go down. So therefore, we could say that resistors 4 and 5 are also connected in parallel. Right. So if we are going to simplify these this original circuit, we could actually have something like this. If this is point A or terminal A, then we could have a parallel combination of resistor 1 and 2, which we are going to call R12 because it's a combination of resistors 1 and 2. And then we have R3 here, so at this point we have R3. And then another resistor, which is the combination of resistors 4 and 5, and we could call that 4, 5. This is point A, and that is point B. Now at this point, it would be so easy to determine that R12, R3, and R45, they are all connected in series because as what you can see, charges can easily flow from A to B with only one path. And therefore, we could just solve the equivalent resistance of these three resistors using the formula RT is equal to R1 plus R2 plus R3. Again, this is because R12, R3, and R45. Again, this is because R12, R3, and R45 are in series, and this is the formula in solving for the total resistance of resistors in series. So let us now solve for R1 and R2. Now R1 and R2 again are connected in parallel, so we could just use the product over sum rule, so that if we will have R12 is equal to the product of R1 times R2 divided by the sum of R1 and R2, and that's going to give us the product of R1, so that's 12 multiplied by 6 divided by 12 plus 6, and this is going to be equal to 72 over 18, and that is equal to 4. And once again, this is R12. Now R3 is just equal to 5 ohms. So by the way, this is 4 ohms. R12 is 4 ohms, and R3 is just equal to 5.00 ohms. Now let us solve for R45, since R45 is the combination of resistors 4 and resistor 5, and they're in parallel. So again, we could just use the product over sum rule, so that's R4 multiplied by R5 divided by R4 plus R5, and that is equal to 4 multiplied by R5 is 8 divided by the sum of resistor 4, so which is 4 ohms plus 8 ohms, and this is equal to 32 over 12, or is equal to 8 over 3 ohms, and that is our R45. So let us plug it here into our equation for the total resistance. So that would be 4 ohms plus R3 is equal to 5 ohms plus R45 is equal to 8 over 3 ohms, and this is equal to 35 over 3 ohms, or 11.7 ohms, as we should express our final answer in 3 significant figures, as the number of significant figures is also 3. So again, RT, or the total or equivalent resistance, is 11.7 ohms, but 35 over 3 would also be acceptable. Now let us proceed to question B. If a voltage of 40.3 volts is applied between points A and B, find the current in each resistor. Now this question may be a little bit tricky, but once you get the hang and the trick on how to solve this problem, everything becomes very easy. So the first tip that I would give you, and I would need you to take in or bear in mind, is to redraw this complex circuit into a much simpler one, whether it's a simple series or a simple parallel circuit. So we labeled this as R1, R2, R3, the 5 ohm resistor, and the 4 ohm resistor is R4, and the 8 ohm resistor is R5. And we could redraw this complex circuit into a much simpler series circuit, wherein this is our R1, rather R12, and we have here our R3, and this is our R4. R45, where R45 is a combination of resistors 4 and resistors 4 and 5 in parallel circuit, and we were able to solve for the total resistance, and that is equal to 11.7 ohms. We are also given in the problem the voltage across A and B, so that is in fact our total voltage, and that is equal to 40.3 volts. Now at this point, since we have the total resistance and we have the total voltage, then we could also solve for the total current. And how do we do that? Using Ohm's law. So total current is just equal to total voltage divided by the equivalent resistance, and here our total current is equal to 40.3 divided by 11 in fact it was actually 6666, so we rounded off as 11.7 ohms, and therefore our total current is just equal to, or approximately equal to, 3.45 amps or ampere. Now at this point, where you have the total current, the total voltage, and the total resistance, you ask yourself, you refer to the last illustration that you had, what kind of circuit is this? Is it a series or a parallel circuit? And obviously, looking at this one, it's a series circuit. Then you would have to ask again, what quantity is the same for all of them? Is it total resistance, total voltage, or total current? So since R1, 2, R3, and R45 are in series, then we could say that the total current is just equal to the current through resistor 1, 2, and that's equal to the current through resistor 3, and that's equal to the current through resistor 4, 5. Again, this is a property of resistors connected in series, that the total current is the same for all of the resistors connected in series. Therefore, we could say that the total current, which is 3.45, is just equal to, which is 3.45 ampere, is just equal to the current through, or 3.45 ampere, is equal to the current in resistor 1, 2, and that is also equal to the current in resistor 3, and that is also equal to the current in resistor 4, 5. That is the reason why if we look at the 5 ohm resistor, which is resistor 3, this is resistor 3, this is the current through resistor 3, and that's equal to 3.45. So now that we have I3, then we could actually solve for V3, even if it's not being asked in the problem, but it might be asked in some other problems to solve for the voltage across V3. And how can we do that? Very easily. We have I3, which is equal, we already have I3, which is equal to 3.45 amperes, and we also have the value of R3 or the resistor 3, and in this case that's actually equal to 5 ohms. So we could solve for V3. How? We just use the we just have to use the Ohm's law. V3 is equal to, according to Ohm's law, it would just be equal to I3 multiplied by R3, and that would be equal to, the current is 3.45 multiplied by the resistance, which is 5 ohms. Then our V3 is equal to 17.25 volts. So we have solved for the current that passes through R3, which is the 5 ohm resistor. And now we would proceed to solving for the current through resistor 1, resistor 2, resistor 4, and resistor 5. Let me just label that R1, R2, R4, and R5. Again, we will just draw the simple combination of these 5 resistors, and in this case we were able to simplify it by having 3 resistors in series. This is R12, this is R3, and this is R45, and the values of the following resistor, R1, R2 is 4 ohms, R3 is 5 ohms, and R45 is equal to 32 over 12 ohms, or we have 8 over 3 ohms. We also have solved for the total resistance RT, and that is equal to 11.666 ohms or 11.7 ohms. And our total voltage is given as 40.3 volts. Okay, 40.3 volts, and we were able to solve for our current to be 3.45 amperes, and this is just equal to the current through resistors 1 and 2, current through resistor 3, and current through resistor 4, 5, mainly because resistor resistor 3, and resistor 4, 5 are in series. Alright, so now let's look at resistor 4 and 5. We have, what we know about resistor 4 and 5 are the following. So resistor 4, 5 is equal to 8 over 3 ohms. We also know that the current through resistor 4, 5 is equal to 3.45 amperes. So from here, we can solve for voltage for 5. And how do we solve for voltage for 5? Recall Ohm's law. So voltage is equal to IR. So we just have voltage for 5 is equal to current for 5 multiplied by resistance for 5. And we have this information. Current for 5 is 3.45 ampere multiplied by the resistance for 5, 8 over 3. That is equal to 9.2 volts. So now that we have voltage for 5, we actually have resistance, current, and voltage. Then you have to ask, what kind of combination does this R45 come from? So if we're going to look at the original illustration, R45 is actually a parallel combination of R4 and R5, and in the parallel circuit you again have to ask which of these quantities would actually be the same for 4 and 5. So since resistors 4 and resistor 5 are in parallel, that means that the voltage across resistor 4, 5, or the total voltage, is just equal to the voltage across the 4th resistor, and that is equal to the voltage across the 5th resistor. Again, this is because resistor 4 and resistor 5 are in parallel. So if they are in parallel, the total voltage of these two resistors would be equal to the voltage across each resistor. This means This means then that the voltage across the fourth resistor and the voltage across the fifth resistor is just equal to 9.2 volts. Then we have the following information. We have R4, which is equal to 4 ohms. We also have V4, which is equal to 9.2 ohms. Then we could easily solve for I4 because I4 is just equal to V4 over R4, and substituting the values, again I'm using Ohm's law to solve for current through resistor 4. So I will have 9.2, which is voltage across the fourth resistor, divided by R4, which is 4 ohms, and that is equal to, divided by 4, that is equal to 2.3 amperes. And if we're going to look at the answer here, the 6 ohm resistor, or rather the 4 ohm resistor, will have a voltage or current of 2.3 ampere. Moving on, let me just redraw our complex combination of the resistors in this problem. So we were able to come up with a simple series combination wherein this is our R12, R3, and R45. Let me just label it. This is R12, and we were able to solve it to be 4 ohms. R3 is just equal to 5 ohms, and R45 is equal to 8 over 3 ohms. We were able to solve for the total resistance in the first problem, or in problem A, and that is equal to 11.7 amperes. And we are given the total voltage in problem B, that is equal to 40.3 volts. So therefore we were able to solve for the total current, which is 3.45 amperes. And since resistors R12, R3, and R45 are in series circuit, so we were able to say that 3.45 is just equal to I12, that's equal to I3, and that's equal to I45. Now we were able to solve for V45, and that is equal to 9.2 volts, mainly because we have the values of R45, I45, so therefore we were able to solve for voltage 45. And remember that R45, this resistor here, is just the parallel combination of these resistors. And in a parallel combination of resistors, the voltage across each resistor is the same, so therefore V45 is just equal to voltage 4, and that's equal to voltage 5. Then we could solve for the current through the fifth resistor, which is this resistor over here. How do we do that? We have R5, and that is equal to 8 ohms, 8.00 ohms. We also have voltage 5, and that is equal to 9.2 volts. So that's 9.2 volts. Then we could solve for the current through the fifth resistor. How? By using Ohm's law. So that's V5 over R5, as that is equal to, and that is equal to I5. So voltage 5 is equal to 9.2 volts divided by the resistor of the the resistance of the fifth resistor, or R5, that's equal to 8 ohms, and that would be equal to 1.15 amperes, which is this answer over here. So now let us look at the current and voltage of this combination over here. Again, recall that our simplified combination for this example is a series combination where this is R1, R3, and R45. R12 rather is equal to 4 ohms, R3 is equal to 5 ohms, and R45 is equal to 8 over 3 ohms. In part A, we were able to solve for the equivalent resistance, so that's R total is equal to 11.7 ohms. Part B gives us the total voltage, which is 40.3 volts, and we were able to solve for the total current because we have total resistance and total voltage. Then we could solve for the total current, and we were able to get 3.45 amperes. And since R12, R3, and R45 are connected in series, therefore the current through R12, current through R3, and current through R45 would be equal to 3.4 amperes. So now let's look at R12. So we have R12 that is equal to 4 ohms. We also have I12, or the current 12, and that's equal to 3.45 amperes. Then we can solve for voltage 12. How do we do that? Use Ohm's law. So that would be voltage. Recall that voltage according to Ohm's law is just equal to IR. So we have voltage 12 is just equal to current 12 multiplied by R12, and we have these information, so therefore our current is 3.45 multiplied by our resistance, which is equal to 4, and that is equal to 13.8 volts. Now remember that R12 is just the parallel combination of resistors 1 and resistors 2. Therefore, we can say that if V12 is equal to 13.8, and if resistors 1 and resistors 2 are connected in parallel, therefore V1 is equal to V2, and the value of that is equal to 13.8 volts. This would then allow us to easily solve for the current through the 12 ohm resistor, because we have R1 that is equal to 12 ohms, and we also have V1 which is equal to 13.8 volts. So how do we solve for I1? That is just equal to V1 over R1, and that would be 13.8 volts divided by 12 ohms. That is equal to 1.15 amps. So this is our current across the 12 ohm resistor, and that is the answer over here. So finally, we can now solve for the current through the 6 ohm resistor. Recall that from this complex combination of resistors, we were able to come up with a simple series combination of resistors R12, which is equal to 4 ohms, R3, which is equal to 5 ohms, and R45, which is equal to 8 over 3 ohms. Previously, we were also able to solve for the voltage across this combination, here, this combination, which is parallel combination. We're able to solve for its voltage, and that is equal to 13.8 volts. And since R1 is actually the parallel combination of resistors 1 and resistors 2, therefore voltage 1 is equal to voltage 2, and that is equal to the total voltage of the combination of V1 and V2, that is equal to 13.8 V. So now we can solve for the current through the 6 ohm resistor. We have R2, which is equal to 6 ohms. We have V2, which is equal to 13.8 volts. Then we could solve for I2 using Ohm's law, and that is just equal to V2 over R2. Then that will be 13.8 volts divided by 6 ohms, and that is going to give us 2.3 amps. Now at this point, you now have the voltage, current, and resistance of all resistors. So if there was a part C in this question, they could possibly ask you for the power. So for example, what is the power delivered by the second resistor, or P2? Then what do we do? P2 is just equal to I2 V2. And what is our current? Current for the second resistor is 3.2 multiplied by the voltage, which is 13.8 volts. Then P2 would just be equal to 13.8, that is equal to 31.74 watts. And that is how we can solve for power. In solving problems like this, it is very essential that we need to take note of the following points. First, simplify the complex circuit in such a manner that you will have a simple series or a simple parallel combination of resistors. So if we have this, for example, resistors 1 and 2 can actually be combined as one since they are resistors connected in parallel. And we have resistor 3 over here, and this one here is resistor 4 and 5. So a parallel combination of these two resistors. Now identify and solve the current, voltage, and resistance for every resistor in each step, and we can do this by asking the question, what kind of combination is this? So we would ask this question, what kind of combination is this? Now we could see that it is series. Now if series, the current of the combined resistor or current of the combined resistors is the same as the current through each resistor. So for example, the current here, if we call that current total, it's just equal to the current I2 is equal to current current 3 and current 4, 5. If we call this R1, 2, R3, and R4, 5. Now, if parallel, the voltage of the combined resistors is the same as the voltage across each resistor. So for example, we'll look at this combination over here, resistors 4 and 5. So the voltage across the resistor 4 and 5 over here, the voltage here, is just equal to the voltage across the 4th resistor, and that's equal to the voltage across the 5th resistor. And that concludes this tutorial. Once again, always remember, physics is easy with Mr. Jesse.